A lot of times here in these types of calculations, we're doing simple algebra like we're talking about here, multiplication, division, addition, subtraction, but we can also get more into conversions, and so that's why we need to look at exact values. And I like to call these really, this idea of conversions. Or going from one unit to another. And so with exact values, these are basically defined values that are basically infinitely known. Basically, that means they have no effect on sig figs in calculations. And, some examples of that would be, well, there are 12 inches in 1 foot, right? That would be a, American or English type thing. We then have, same idea, but maybe more in terms of metric. 1,000 meters equals 1 kilometer. So these ideas are infinitely known. And really what this is a conversion. Right? If I want to be in inches, or do I want to be in foot or feet? Do I want to be in kilometers, or do I need to be in meters? And so basically these are conversions for us, and they have no effect on sig figs as far as the calculation goes. So let's look at an example here of metric to metric. And so here we want to convert 5.23 times 10 to the 8th nanometers to centimeters. So in order to do this process, I kind of like to think about where we're want to end up and where we're beginning from. We're trying to finish with this idea of centimeters, and we're in this term of nanometers. And while this process is difficult, in order, going from one directly to the other, something that's easier is relating it first to the base unit, and our base unit here would be meters. And then second, take the base unit and relate that base unit to desired unit. And that would be really step 2 in terms of these, types of, simple metric conversions. So this is where this notion of dimensional analysis comes into play, where if we, really show units as numerators or denominators, you can follow the transformation or follow the conversion from one unit to another. And so the first place that we want to begin with here is start with the measurement. And our measurement from above was 5.23 times 10 to the 8th nanometers. And notice that I'm really showing the numerator and the denominator as far as that goes. Right? I have my denominator, which would be on the bottom. And then I have my numerator on the top. And that's going to be important for watching these things cancel out. So step one was looking at going to meters. And if we look up our conversions, we would find that for every 1 nanometer, there's 1 times 10 to the negative 9th meters. And so this is our conversion. Notice that what's happening here is the units are canceling out. Our original measurement had nanometers, and so now that's going to cancel because we're dividing by nanometers in terms of that unit. And so now what we're left with is in terms of meters. That was step one to get to the base unit. Step two, now we're going to the desired unit. Again, we write our fraction as a conversion. We're trying to go for from centimeters to meters. From meters to centimeters. And for every 1 times 10 to the negative second meters, that is 1 centimeter. So again, here is another conversion where now our units of meters is canceling out with this conversion piece of the meters. And the unit now that we have left over is centimeters. So this is getting to our desired unit. And now we're at our answer here, where if we do that calculation, we would end up with a value of 52.3 centimeters. And so that is our final answer. We started with 3 sig figs. We should have 3 sig figs as well. And this is based off the measurement. The conversions that we did, conversions had no effect. So keep that in mind. Let's do another example, but let's do American to metric. So here in this example, the 100 meter dash is how many feet long? So realize that, you may have to look up these conversions, and that's okay. But if we think about our process again, where do we want to end up in this process? Is we want to end up in terms of feet. And we're starting with this idea of meters. So here's the start. Here's the finish. And so between those two, since you're going, from different style units, you need to find the connection between the two. For instance, I would say that, there are 2.54 centimeters in 1 inch. So that would be my kind of conversion point between the two, is realizing that I can go from that idea of centimeters to inches. And now hopefully that sets, kind of the game plan. At first we want to just go from meters to centimeters. Step 2, we want to use that conversion. And now we're converting between inches and feet. So we set that up again. We want to do just like we did before. We want to start with the measurement. And that measurement was the 100 meters. Again, accentuating the numerator and the denominator there. And so for step 1, I want to go from that idea of meter to centimeter. So for every 1 times 10 to the negative second meters, that's 1 centimeter. So there's my conversion. And I'm canceling out my meters and going into the unit of centimeters. Now I'm going to step 2 from above, where now I'm using that connection between two different style types. I just want to make sure that I have the units in the right place. So I want to go from centimeters to inches, so that's why I'm putting the centimeters in the denominator, so that cancels out with the centimeters in the numerator in the first part. So now we've canceled from centimeters, and now we are in terms of inches. And step 3, now we're going between those two units, the final unit, which is feet or foot, and they're 12 inches in a foot. And so that is our last conversion here, with inches canceling out. And that gives us a value of 328.0839. There's probably some other digits there. Feet. Look at our original measurement. Right, with the 100 meters, that's equal to 4 significant figures. So we're really looking at cutting this number off at the 0. And so that means our final answer would be 328.1 feet with our sig figs. All right, let's look at another example, and let's still look at this idea of American to metric, vice versa. Basically going in between two different styles of units. But let's up the ante a little bit. The velocity of sound is 767 miles per hour. What is this velocity in meters per second? So the difference here now is that we actually got two units, right? We have a numerator and a denominator. And so how do we work that? So in the beginning, there's two conversions going on. Just pick one to begin with. Then go to the other. Meaning that if we look at where we want to go, we're trying to get to meters per second. And where we're starting off at is miles per hour. So here's our initial, and here's our final. So we also still have to do this notion of, finding the interchange between different styles of units. So in this particular case, there are some conversions, such as for every 1 mile, that's 5,280 feet. And that for every 1 meter, that's 3.28 feet. Again, these are values that we can look up, right? We don't have to memorize these conversions. So if we know that type of interplay, that if I can go from, for instance, the bottom isn't the hardest, right? We probably could go in step 1 to miles per second, because we know how many hours or minutes are in an hour, how many seconds there are in a minute. And then we can enter this interplay between saying that, okay, well, from that I can get to then feet per second. And then I can get to our final answer after that with that third conversion. So that would be using the 1 mile to feet conversion second, and then the 1 meter to feet conversion third. So it's finding that interplay, which is really important in terms of going from one unit that you're familiar with to maybe another one that you are not. So we can start with that measurement. That measurement, right, being the 767 miles per hour. And so for step 1, for every 1 hour, there's 3,600 seconds. So there's our first conversion. Allowing now for hours. Even though the hours is in the denominator, again, we still have that idea of it canceling out with something in the numerator. So now we're technically in miles per second, which now takes us to step 2, where we're going to look at feet per second. We were in miles, and we're trying to get out of miles. We're trying to get into meters. So we've already converted to our seconds, so we are good with the denominator conversion. It's all set. But now we need to concentrate on the numerator. So we would go to that feet idea, that for every 1 mile, there's 5,280 feet. So here is our next conversion. Notice that's canceling out with what we started with at the very beginning, that's 767 miles. The miles is canceling out with the denominator in the conversion. And so now technically we'd be in feet per second. And now we're jumping style of unit with step 3 to get to meters. And from that conversion above, for every 3.28 feet, that is 1 meter. And so that is our final conversion. Feet now canceling out. And we're left in that finally the desired units, because if we look, we have now meters in the numerator, and we have our seconds in the denominator. So if we calculate that out, we get a value of 342.96747. Again, I'm sure it goes on. Meters per second. Right, the original measurement. Right, the 767 miles per hour only has 3 sig figs, so we should be looking at this number for our boundary of units, and so that means our final answer would be 343 meters per second. This example gets into now multi-dimensional units. Then we can think of, multi-dimensional units as, meters squared, meters cubed, etc. As far as, not just seeing meters, but actually 2 sets of meters or 3 sets of meters. So, what we have to be careful with multidimensional units, in conversions, you need to do the conversion in each of the dimensions. Meaning, you have to square or cube the conversion to be correct. So let's look at an example of this. What is the volume of a room? And that's going to be specifically in liters. That measures 8.28 meters by 10.9 meters by 4.44 meters. So there's our question. What is the volume of a room that measures these certain dimensions? So if we look at again our method, all right, we're looking to get to liters as our final objective here, and we are starting with measurements, right? Basically, we have a length, a width, and a depth, if you will. So hopefully that's setting us up for the idea of multidimensional conversions, meaning that if I go to step 1, I could get into a unit that is multidimensional, namely meters cubed. And so then the question is how can I get to this other unit of liters? Technically, these are both scientific international units. But for the interchange of volume, I like to use the centimeter cubed is equal to a milliliter. So if I can get my meters cubed into centimeters cubed. And now I can go to that other style of unit, namely this volume in terms of liters or milliliters. That I can now finally get to my answer. So once I'm into the milliliter unit, I can then get to the base unit of liters after that pretty easily. So here we have to start with our measurement, which is really step 1 above, right? We have to take the length times the width times the depth. So we'll be taking that 8.28 meters, multiplying it by the 10.9, and then by the 4.44 meters to get a value of 400.7188 meters cubed. It goes on further than that, so you should remember to keep, all the digits in terms of the calculation. I'm being a little bit shorthand here. There's some more. But at least that gets us to a reasonable set of units to go forward in the calculation. And so now that we have that done for step 1, now there is our measurement. So we're going to start with that 400.7188 meters cubed. And so I'm trying to go between a meter and a centimeter in one dimension. So here is our conversion. But realize I need to have that conversion cubed. All right, because I'm trying not to go between meters and centimeters. I'm trying to go from meters cubed to centimeters cubed. And so that allows me to get into centimeters cubed. Now that was our step 2 in that process. Again, the big part of this was the multidimensional conversion. And now we're looking at step 2 here with the conversion of 1 centimeter is equal to 1 milliliter. So we've now, that should be centimeters cubed. I apologize. 1 centimeter cubed is a milliliter. So that is canceling out. And now we're going to the liter unit. There's 1,000 milliliters in a liter. And so that is our last conversion to get into the proper units of liters. And that gives us a value of 400,000 718, sorry, I was reading my notes here. 718.8 liters. If we go back, our original measurement was 400.7188 meters cubed, but if we look at those values there, right, going up to the top, we should have curtailed this at the ones place, because all of those measurements have 3 significant figures. So that means that our measurement really is in terms of 3 sig figs. And so now we can look at that number as 401,000 liters, or we could look at it as 4.01 times 10 to the 5th liters, right? It's getting into a larger unit. So either one of those would be acceptable here for this conversion. In this example, I'd like to look at just specifically a temperature conversions, because these involve equations. So when looking at these temperature conversions, the values that are already part of the equation do not have any effect on basically the number of sig figs. In that answer that we're looking for. So that's the idea. With temperature conversions, we have basically two styles, if you will. Right, we have degrees Fahrenheit and degrees Celsius conversion, which looks like this. And then we also have the idea of Kelvin. And Kelvin is your degrees Celsius plus 273.15. And so these are our temperature conversions. But notice that our values within the equations, like the 1.8, the 32, the 273.15, and they just don't affect the actual number of sig figs at the very end. So let's do an example as far as let's calculate the boiling point for liquid nitrogen in degrees Fahrenheit and Kelvin. If it boils at negative 196 degrees Celsius. So doesn't matter how we want to start here. I'm going to start with equation 1. So I'll start with the degrees Fahrenheit. We're just really kind of plugging these values into our expression that we see above. Like we see here. And if we plug that in, we should get a value of negative 320.8 degrees Fahrenheit. But in this case, right, our measurement is negative 196 degrees Celsius. So there's only 3 sig figs there. So we would be cutting the number there at the 0 or the 1's place. So So our final answer would be negative 321 degrees Fahrenheit. So simple equation, not too difficult. Just realize that the other two numbers don't have an impact since they're part of the equation. It's only the measurement that is important. Well, for step 2, we'll now get at the idea of Kelvin. So our Kelvin would be equal to our degrees Celsius plus our 273.15, and if we do that, we get a value of 77 Kelvin. That is our answer, right? The measurement here, the negative 196, is accurate to the ones place. And that's what we see in our actual answer. So remember, they're different if you're talking about multiplication, division versus addition, subtraction, right? So I'm just trying to reemphasize that idea with the accuracy of the measurements. And that's temperature conversions. Now that we've done a bunch of conversions, we're into really our first physical property. And our first physical property is density. Right? Density involves just, basically this idea of a mass to volume ratio. So check out this Coca-Cola experiment, and we can come back and revisit this idea of density because it really answers, the question, which will float? A full can of Coca-Cola or a full can of Diet Coke? Or will they both float? Or both sink? Check this video right here. Maybe think about it a little bit, have a hypothesis, and see what happens. All right, now we're back. Right, the answer, right, is that the Coke can sink while the Diet Coke can float it. And we might ask another question, why? And the answer is different densities. Right, what's the difference between the two? The Coke can has sugar, right? Lots of sugar. While the Diet Coke can does not. So basically what we have is more mass per volume, this is greater density. While on the Diet Coke side, we have less mass per volume. And that's now less, or smaller, I should say, density. So that's the kind of the idea of density. There are some subtly different units that we have. Density is given this moniker small little d. Oftentimes there's some descriptors that are there. The top being the temperature at which this density applies, the molecule or element as far as what that density is describing. The density of water is equal to 1.00 grams per milliliter, but this is a conversion for us, okay? So it has no impact on units as far as sig figs or numbers of sig figs. So again, conversions, no effect there. So that's our density. We do find subtly different units in going through density. Density of gases tends to be grams per liter. In terms of the volume is different. The density of liquids tends to be grams per milliliter, and the density of solids tends to be grams per cubic centimeter. And realize that the milliliter and the cubic centimeter are the same thing, right? We did an example earlier of that. So what is this good for? Well, this is now a conversion that lets you go between different types of units. In this case, mass and volume. So far, all of our units have been going to similar styles, as far as length or volume to volume, length to length, etc. And now we're actually going between two physically different styles as far as our types in terms of a mass idea and a volume idea. So this is really advantageous to us because this basically means that if I weigh out a material, a molecule, right, I automatically know its volume with this idea of density. Or if I, measure a volume, I know its mass. And again, the mass will become important, in terms of moles. But this is allowing us to go between two intricately different style of units, mass and volume. So let's look at an example of this. Okay, so here's our question. How many liters of benzene are there in a container that holds 25 pounds of benzene? Benzene has a density of 0.874 grams per milliliter. And so, again, let's look at our idea of where we want to end up, namely at liters, and where we're beginning, which is at pounds. And so as you can see, we're going between two distinct different styles of units, right? First thing to realize is looking at our values. We're talking about going between a mass and a volume. So we need to have a mass to volume exchange or use density. So that's probably going to be coming somewhere in the middle of the equation, right? If I think about the density value that I have, and now boxing that off to the right, as far as a conversion, if I come backwards from liters and get to milliliters, well, that is where that interchange could be in terms of the conversion of grams over milliliters that we're seeing below here, right? This mass to volume exchange. So the question would be, if I can now know to use density in that way to get to the final answer, well, that means I just got to get my mass in terms of the correct answer. And so, maybe a hint that would help in that process is that there's 454 grams in every pound, right? So again, that's something that we could look up. And so that's allowing us to get to that gram per mil conversion, which would be really step 2. And then once we're at that conversion, we can go finally to our answer with step 3. So going all the way to finally liters. So that's the idea. We still want to do the same exact notion as far as all these others, which is start with the measurement. And our measurement here is the 25 pounds. So if we go to our step 1, where we're converting out of the pound, getting into grams. So there's our first conversion. We then go to the second step, which is now using density in such a way so that we convert from the mass unit to the volume unit. So we would want to have our 0.874 grams in the denominator and our milliliter. So that's our conversion in terms of that mass to volume idea. And I'm just arranging the units in such a way so that the correct unit cancels out, namely mass. And now we're in the correct unit of volume, namely milliliters. So that takes us to the third step, where now we're converting from the milliliter unit to the actual liter unit. And so that gives us an answer of 12.98627 liters. Remember our measurement, which was what, the 25 pounds, only has 2 sig figs. So we would be cutting the number here at the ones place. So our final answer would be 13 liters. And so now that's just upping the game a little bit by now showing that we can go between completely different measures of units as far as mass and volume. We'll find others are out there as well, especially when we get into the notion of moles. Look for that soon.